Oh me, oh my, good morning. I won't dally. Today's a big lesson, so, graphs. Many graphs. Alright, so, specifically 3 types of graph. Position with time, energy graphs, and PV graphs. No worries, it'll take short breaks in between to not overwhelm you. Also, it should be a really fast explanation. First, position graphs. Okay, so when looking at any graphs, you should first try to understand what the axes mean. Here we have position over time, which means that a thingy has a certain position at a certain time, and the slope of this line is the velocity, because if you look at the axes and use change in y, which is position, and change in x, which is time, you'll get an answer that is in terms of distance over time, which means it's a velocity. Going a level deeper, there's also velocity over time graphs, but it's the same concept. You only imagine that instead of being at a certain position at a certain time, an object has a certain velocity at a certain time. Alright, let's step into those velocity graphs real quick, and let me tell you a secret. Lean in close. I'm giving you a calc lesson because calculus is the study of slopes, and slopes, aka the derivative of a position graph, is the velocity graph, which means that the area underneath the velocity line is your change in position on that interval, because that's the integral of the area under the curve, which would mean we're going back into the position of the graph. Okay, it's break time. I need this as much as you. Here's some soothing jazz for a couple seconds while I present you an image of this bee flying around. Okay, I'm calm now, so moving on to energy graphs. If you don't know anything about energy or joules or the types of energy, which are usually kinetic and potential, and sometimes heat, then too bad. I'm going to talk about them anyway. So, graphs involving energy are usually energy over time or energy over position. So let's talk about energy over position. First, remember that cool law that says energy is conserved? So when the energy isn't seen on the graph, it exists as a different type of energy or has left the system. Looking here, we can see there is a hump. Where the hump exists, it shows us that there's a maximum amount of this kind of energy, which means that for the rest of the graph, if we're not losing energy in the system, there will always be this total minimum energy of that value. So, like here, we have this much potential energy and this much kinetic energy, which always has to add up to the total amount of potential energy showed on the graph, or at least that. Knowing energy, you can calculate height or velocity, which is cool. Enough graphs. Let's look at something not graph related. It's break time. Like this. Oh no, not that. How about a violin? No, what's happening? No. Slippy slides? I can't win. Okay, that was a weird break. So, PV, or pressure and volume graphs, usually involve the ideal gas laws and processes. Lots and lots of processes. Work done on a system here is the area underneath whatever the line is you make. The only things that make a point change here are volume, pressure, and temperature? What? Temperature affects a point on a graph that never says it's about temperature? Yeah. Because science. And there's your rundown on graphs. Now, if you take anything away from this, let it be this. Flossing is insanely important to maintaining proper dental health. Good morning.